This is actually, this work, ADR-X, is actually work done largely by the efforts of Hao and Murali, two research interns at, in the Xbox team. Unfortunately, they were not able to make it here today, so I'm presenting for them. I'm hoping many of you play Xbox here, right? Any hands up here? Some of you should actually go and play more, I think. Anyway, so yeah, I mean, if you're into gaming, you'll probably appreciate this a lot more, but nevertheless, it'll be interesting, I'm hoping. So there are three things I want you to sort of remember in this talk. The first is real time, in the sense gaming systems, as you can understand, are real time. Every millisecond counts here. They are, power and compute constrained. Most of these devices are embedded devices. For example, Xbox uses 150 to 600 megahertz ARMS controllers, so you don't have infinite resources to do stuff. And last but not the least, every design decision that you do in building these systems is governed by user experience. That's what matters at the end of the day. So I hope you've got that baseline. I'll quickly go over how a game engine works. Essentially, game engine is just infinite loop that evolves game state using physics or some other mechanism. So game state can be things like locations and velocities and all those kinds of various game objects, essentially. So that's what it does. When a gamer interacts with the game, they use controllers or joysticks and things like that. They press some buttons. These are transmitted as inputs to the game engine. The game engine then evolves the game state based on these inputs. Sometimes, you also get feedback from the game engine. For example, let's say bomb explodes. You'll see some vibrations in your gaming controller. That's because haptic feedback has actually been transmitted from the game engine back to the controller. Last but not the least, audio and video frames are generated, some of which go to the screen, some of which go to the headset, and so on. So this is roughly, how a game engine usually functions. Now, to emphasize more on this, the fact that we are power constrained, controllers come with batteries, and so most of these controllers and embedded devices actually follow a sleep cycle, right? So out of, for example, typical Xbox, there is a cycle of about 8 to 16 milliseconds, and you're awake for about a millisecond. In that millisecond, you'll have to process everything, do whatever you want with the inputs, and then transmit that back to the game engine, and then you go to sleep, right? Okay, so this group, I'm sure, understands why people prefer wireless. You probably love wireless. But the truth is that most of the gamers, like professional gamers, they actually don't use wireless. They like to not use wireless. And that's because of the distractions that come because of artifacts generated due to packet losses. To give you a sense of how it looks, what I've done, these are actually actual game traces that we have collected. When you have a packet loss, it exhibits itself as a silence period. So you see that straight line there, that's actually a silence period. And to a player, it'll sound like glitches. What I'll do is I'll play one 10% loss. This is easier for most people to detect. I don't know, it's too low volume, I'm guessing, right? Anyway, so you should take my word for it, I guess, that you start hearing these glitches when this happens, and it's distracting for people. This is sort of what happens in video, 0.5% loss, which is actually very low. You can start seeing artifacts already. This is very visual, so you're probably seeing that, right? On the right hand side, these are actual game traces, right? Now, one of the things that you see in many of these user studies that people do in terms of the effect of packet losses on games is that they assume uncorrelated independent packet losses. So that's a very common thing that people do. But through our studies, whatever we did on actual user traces, we found that this is not true. In fact, losses occur in bursts. It's very common to see 2 consecutive packet losses or 3 consecutive packet losses, as seen in this histogram out here. And so what we did is we conducted our own study in which we actually we took lots of famous games that for Xbox as well as VR and so on, and conducted a user study on top of that. And not very surprisingly, what you see is essentially anything above 0.5% loss, both in audio and video, people start experiencing artifacts. So this sort of sets as a standard. This is where we want to go. Ideally, even lower than 0.5%, but at least that's the baseline, right? And we can't have consecutive packet losses more than 16 milliseconds. The moment that happens, you start to detect that. So let's try and understand what happens in a wireless channel during gaming, right? This is how he is playing this game in his lab, fun project. And this is Grand Theft Auto he's playing. And he's about 3 to 10 feet away from the receiver. So it doesn't seem like he's too far away. Things should be fine. This is a Wi-Fi connection. So what I'm drawing here, this heat map actually indicates the subcarrier SNR. So on the y-axis, you've got subcarrier SNRs, and on the x-axis, you've got time. So in the first 2 seconds, the controller is static, lying on the table. Nobody is walking around, no environmental changes, and so on. So you can see a very steady sort of SNR. Yellow represents very high SNR value, and so on. The next 2 seconds, How walks in, he's walking around. The controller is still static, by the way. So you can start seeing some changes. This is because of multipath changes in the room. Finally, at the 4th second, he actually starts playing the game Grand Theft Auto. And at this point, he's trying to, taking the controller, agitated, pressing buttons and stuff like that. So he's actually moving it actively, right? So what you notice here is things start to dramatically change. You see more blues there, SNRs have dropped down, lots of quick changes, and so on. And this is still at 3 feet away, right? Now, what I've also drawn to quantify this better is this black line in the middle graph that you're seeing is the 50 percentile SNR across all the subcarriers. So what you see is the same trend, which is as soon as it starts playing, you see that the SNR is really gone low. And here I'm also indicating retransmissions, packet retransmissions, which are indicated by yellow lines, and packet losses by red lines. So you can see everything go bad at this point, right? So now let's see what's the rate adaptation algorithm doing. The rate adaptation algorithm is actually trying to modulate the MCS. It's trying its best. It's trying to catch up, but you can see a lot more variation out here in the last few seconds. Now what I'll do is I'll zoom deeper into this thing. So I'll take 1 second and I'll actually zoom deeper into that 1 second and try to see what's going on. Here if you see, there are the channel is changing by almost 10 to 50 to 80 dB within a small period of about 50 to 80 milliseconds. That's what's really happening. It's changing really fast. Now a curious thing that you see here is in this particular interval, the channel is actually worsening. So there's a downward trend in the SNR, but the MCS is actually going up. That's the upward trend. And that's happening because the channel, the rate adaptation scheme is actually very slow to react. Just before this downward trend started, the channel was actually improving. So historically, it should keep on going, keep on increasing. And so that happens a lot. And the same reverse trend also happens towards the end. The channel is getting better, but the MCS is going down. So basically, these schemes are unable to keep up. So at first when we saw this, we were like, hey, rate adaptation has been out there for 2 decades now. There must be something that we can pick up. More recently, there are also ML papers that are using ML to do rate adaptation. So all we have to do is just pick something up. Let's see what happens, right? And this is what happened actually. We did go about, we tried a lot of different scheme all the way from 1997 when first ARF, the earliest scheme came, to Q-learning based schemes in 2021. So we basically, this is a representative set, but there's more trials that we did. The interesting thing that you see if you can't read the numbers is that pretty much if I close the left-hand side and ask you to read the loss rates in those columns, you won't be able to tell any difference. Essentially, all that 2 decades worth of work doesn't really show much significant difference when it comes to gaming systems, right? And that was also very surprising for us when we started. And also all these numbers are 2 to 4%, which means we still have work to do. We have to go to this 0.5%. So the hope was that we will be able to come up with some kind of a scheme which can even predict what's going to happen looking at the trends and is much faster to react, and it continuously learns what's going on and sort of adapts, right? That's the hope. That's where we want to get to. So the intuition is that the key issue is that the wireless channel has a lot of these hidden latent effects, right? For example, how is the play, what kind of game is it? How fast is the person moving the controller? Things like that. For example, there's interference out there. There is, the device itself has some characteristics. There's so many of these unmeasurable kinds of, effects, and hopefully a neural net will be able to learn all this stuff in a data-driven manner. So that was the hope, that was the intuition that we started from. And we tried a lot of, so I won't go into details here, lack of time, but basically we tried a lot of existing reinforcement learning algorithms, policy gradient and so on. What really worked for us in the end was PPO clip. So this is again the one that they were mentioning in the last talk as well. It's a particularly successful reinforcement learning algorithm. And so you can see in this table, if you can't read, I'll let you know that the loss rates here are actually 10x less. They're 0.13%. Or things like that. So it clearly showed us that there's some benefit to this. But the issue that we faced here was that the runtime of these was almost 17 to 30, 40 milliseconds on an ARM processor. So we really couldn't use this because our budgets are well below 1 millisecond. So we have to get the same performance, but 100x faster, right? So that's the only time that we can put it inside an embedded controller and hope that we can actually use it. So that's where we were stuck with. Now, so we sent about designing, hey, how can we design something that actually runs 100x faster, but actually can get the same performance? Now, the key intuition is that there is a lot of knowledge in the communication theory that we can actually, some domain knowledge that we can actually leverage. And what this will do is ease the pressure on the ANN itself, right? So that was the hope that we're going with. And so the intuition is this, that suppose there were no wireless, suppose there was just a wire, then, well, it's a very trivial problem. You just get the SNR and then you can predict what the PSR is going to be, and then you can just use that to decide what MCS to use. The issue is that there is this wireless channel. So what we do is we came up with this contextual multi-armed bandit that had 3 stages. The first stage's job is just to model wireless. And what it does, it takes in all the wireless channel measurements and converts it into one number. This number is then treated as if it were a wire, right? And so its job is to just basically map all this wireless stuff to a wire. So that's what this neural net is doing. And then after that, you have well-defined packet success rate functions that you can use that convert it into packet success rate. You can predict that, and then comes a multi-armed bandit that basically looks at all these predictions and then decides, hey, what is the action I should take? In this case, what MCS I should book. So that's the high-level architecture of this thing. So this is basically how ADR-X works, right? In the controller setting, controllers wake up, they use this, the contextual bandit to run an inference based on all the history that they've got to figure out what MCS they should use. And then once that's done, they use the policy to transmit away packets. Of course, they may not succeed, they may succeed. That comes as feedback. That feedback is used to do one-step training for the contextual bandit, and then they go to sleep. And so this whole cycle keeps repeating, right? So it's online learning all the way, and you keep learning and inferring and so on. Now, one of the tricky things here is how do you train this thing? So typically you have this neural net and you've got this predictor. The predictor is giving you some prediction, but where is the gradient descent coming from? Where is the error signal? Because you don't know what the actual PSR is to start with, right? So that was one tricky thing we had to solve. But I won't go into the details of the proof and so on, but it turns out that if you actually take the instantaneous value, which is 1 or 0, if you receive a packet, it's 1. If you transmit a packet, it's 1, otherwise it's 0. If you use that, then asymptotically, it will actually converge to the right answer. So that's what really happens. Now, we had to do a lot of feature engineering in order to get it down into that microcontroller. I will not go into a lot of details, but simple things like sort all the SNRs, because the order does not matter in the decoding. Sort all the SNRs and give it, things like that, which really helped us cut down the size of the neural net, history and things like that. Lots of trial and error and trials. One of the very tricky thing was survivorship bias. So essentially, when you lose a packet, you also lose, the CSI measurement that you're getting from it. So you end up getting only measurements from successful packets, and that's really horrible to train your neural net on. The second thing is, this is an online learning algorithm. The person is actually playing the game, and it takes some time to learn. So during this learning phase, it can make horrible decisions. And if it does that, then the player is actually getting a really horrible performance. You can't go to the player and say, hey, wait 40 seconds, your performance is going to really improve. Just keep on going. So that's not going to work. So we needed to, so for this, what we did is we used a very simple guardrail kind of mechanism. So we have a conservative retransmission mechanism, which essentially what it does is basically reduces the rate a lot while retransmitting. And so eventually, of course, this is inefficient when it comes to power, but eventually when it learns, this is not used at all, essentially, right? So this mechanism solves both of the things. So now I have sort of the final result here. What you see in summary is that its performance is almost close to that of PPO, and at the same time 100x better. So in fact, it takes only 170 to 380 microseconds to run on the 400 megahertz microcontroller. Now, how well does it converge? Here are there are many results in the paper, but I've picked like 2 of them to just demonstrate. So here, if you start from scratch, if the weights of the neural net are completely initialized randomly, it takes about 40 seconds, right? It takes a long time. But you can do federated learning. So you can actually learn offline and sort of start from a good point, and then the gamer can start. In that case, it comes down to about 10 to 15%. So 10 to 15 points is actually come below 0.5%, right? It will reach that point. And as you do more and more trials, as the player keeps playing, it improves with more trials. How robust it is, easy to sudden changes. So one of the issues is, of course, sudden change in interference levels. So let's say you go into a really busy channel, you're losing packets even though you're taking the right action, and that confuses the neural net a lot. But over time, it also learns that and becomes very robust to it. So if you see here, it's actually managing to not go above the 0.5 level even when the interference levels change. So that's all I have. There are many more results in the paper you can look at, but in summary, ADR-X is this ML powered adaptive data rate scheme that actually can run on microcontrollers for gaming.